Otherwise, I'll just jump right into it. Hi, everyone. I'm Sam Spaulding, and I'll just maybe give you a couple sentences about my background. I'm currently a character AI researcher at Jibo, and before that, I got my master's degree in the personal robots group at the MIT Media Lab. And while I was there, I did a number of projects that involved integrating Affectiva's emotion analytics into social robots. So I'll tell you about a couple of those projects, and then also kind of, maybe give you a glimpse of the future of what we're trying to do here at Jibo using Affectiva and partnering with them. So let's just jump right into it. Socially assistive robots, educational tutoring, and affective computing. First, let me just kind of get the fundamentals out of the way. What are social robots? Social robots are robots that are meant to interact with people as people. They're meant to be sensitive to the ways that we communicate as humans. Human to human. Most sort of typical robotics research, people think about stable walking, manipulation, kind of doing what robotics researchers call the 3Ds. That is, tasks that are dirty, dull.
Sorry to cut you off there. You haven't shared your screen yet. So.
Oh, I haven't shared it. I'm so sorry. Let me see. Share my desktop. All right. How about now? Can you guys see anything? Yes. Yes. I'm sharing my desktop. There we go.
Yeah. Perfect.
Perfect. All right. Great. Social robots. There we go. So you can see we draw on a number of different fields: AI, robotics engineering, and also studying how it is that humans interact with each other, how humans interact with robots as a form of new technology. And you can see just here at the bottom a couple of the different domains that we work in. So one for education, two for sort of smart collaborative assembly. You got Tony Stark over there with Jarvis, and also as an aging-in-place helper, sort of providing support for the elderly to kind of help them age gracefully. All right. And specifically, one of the subfields that I'm interested in and that I've been working in is the subfield of socially assistive robots. So these are robots that are designed to help people, but not help them through physical interaction or by solving physical tasks, but through social and emotional support. So that is things like education, motivation, healthcare. These are all sort of core application areas for us in socially assistive robots. And these are a few examples of some of the robots that we've built at MIT and that we've actually deployed. So we're very, we're very application driven. You can see kind of up here in the top left, we've got the huggable robot, which is being used at Boston Children's Hospital as sort of a chronic care assistant. We've got this robot, the DragonBot, that has been used as an educational companion, and Tyga down in the bottom right, who I'll talk about and will sort of feature most prominently. That is the first robot that we've really strongly integrated our the Affectiva software into, and it plays a core role in the way that this robot, sort of understands the world around it, understands who it's interacting with, understands how that person is feeling through the course of an interaction, and uses that to kind of influence its behavior. I'll just very quickly breeze through some of these core things. So one of the things that we know about robots is that embodiment matters, that we've seen across a number of studies that having a physical robot body is importantly impacts the way that people relate to robots. And we've seen things like higher learning gains, greater compliance when having to do sort of like a therapy task, forming long-term bonds. And my hypothesis, which we're researching right now, is that the actual physical way that people express and emote with a physical robot is different from the way that people interact with and emote with different kinds of technology. So the way that people interact with a tablet is different from the way that they interact with a book, is very different from the way, and different emotional responses to a physical, socially evocative robot. All right, so let's just jump into education. We have these intelligent tutoring systems. They're kind of educational software that are actually in wide use, and they have a number of great features. I mean, they have very sophisticated artificial intelligence backing it, and most importantly, they've been extensively tested in real-world environments. So they're actually in use in schools, and thousands of kids are using this software. Our goal is to combine the benefits of physical embodiment with a robotic tutor, along with the benefits of that intelligent tutoring system. So if I had to sum up our research goals in one phrase, it would be this one down at the bottom. We want to develop physically embodied robot tutors that can sense and understand the emotions of students, that can build models of these students based on this affective data, and that can act intelligently as a result of the model info. The first project that I'm going to talk about here, we had a child and a robot interact together through this shared story game. So they would, the robot and the child would each take turns creating a story. They would add a line to the story based on how the characters move on this tablet game. So the tablet acts as a shared social context where the robot and the child can interact together. So the child can move characters around on the tablet, and the robot also has control of the characters as well. So the child will move a character and create a line of the story, then the child will do the same and back and forth. Now the robot will ask the child periodically to read a word. You'll notice at the top, the sentence of the story will appear at the top of the screen. So this one, it's got the purple dragon roars. And periodically the robot will ask the child, hey, can you identify the word dragon to me? I want to learn how to read that. Of course, what's actually happening is the robot is asking the child to demonstrate their knowledge of reading. And in a way, the robot is trying to solve this problem. It's an algorithmic problem called the knowledge state estimation problem. And real quick, I'm just going to zoom out and kind of provide sort of a theoretical overview of what this is. For an adaptive tutor, we want to know how do you personalize the curriculum of a task, right? And in order to do that, the tutor needs to know, okay, what does this child know? What does this child not know? This diagram on the right is, it depicts flow, the flow state, right? So a flow state is sort of a zone of optimal challenge where it's not too difficult that you feel overwhelmed, and it's not too easy that you feel bored. It's kind of in this sweet spot where you're challenged, but you're also learning. It's an achievable challenge. And education theorists have, sort of identified this flow zone as sort of the optimal place for a tutor to, introduce new curriculum. All right. I'm going to sort of gloss through the math of this a little bit, but essentially what we've done is there are algorithms for estimating a student's state of knowledge. This is sort of a standard one called Bayesian knowledge tracing. It uses patterns of a child's answers, so whether they got a question right or not right, to sort of estimate whether they know or don't know a particular skill. It's widely used, but it's a pretty sparse channel for estimation, right? I mean, it's only based off of, and it only learns based on whether a child gets a question right or wrong. And so as a result, you have, this leads to a design of software that is heavily based on just having the child answer as many questions as possible. Now, leading education theorists know just asking question after question, that's not the right way to teach a child. Good human tutors also know that that's not the best way to understand what it is that someone does or doesn't know. So what we've done in this project is we introduced a new model that not only does it sort of learn from whether a child gets a question right or wrong, but it learns from affective data while the child is answering the question. So the robot, which we've integrated with Affectiva software, is able to understand whether a child is engaged while answering a question, whether they're smiling during a question, overall what their sort of valence is it positive or negative? And these are obviously, I mean, any human teacher knows these are critical features in understanding how a child is progressing through an educational curriculum. So Affectivi's software has allowed us to sort of take in more information and add that to the robot's sort of wheelhouse of knowledge that it has about how a child is progressing. I'll just kind of quickly go through a few results here that we were able to uncover from this experiment. So we did an experiment. We had 25 children come in. They played this educational game. And then some of them also did it without the robot, with just the tablet. And we were still sensing the affective data, and we wanted to see, you know, is the data that we get with a robot or without a robot the same or different? How can we really quantify, you know, the emotional impact of having a robot play the role of the tutor in this interaction? This is kind of the data workflow that we ran through. So we took these still frames of video, we ran them through Aftex. This is, you know, kind of a sample of what the signal looks like, affective data, especially at a high frame rate. You know, it's going to be noisy. We smooth that through a median filter, and we end up with a little more sensible signal. So it kind of just smooths out those oscillations. But the end result is that you can be a little more sure that when you actually see a peak or a trough in the signal, it's a genuine thing and not just an artifact of the sensor. We take this average value overall, and we sort of compress that down into a mean metric value. All right, so here's the first of the results that I want to talk about. We're able to show here that across a wide variety of affective metrics, the participants were more emotionally expressive when they were interacting with the robot compared to when they were interacting with the tablet. And you can see it's most pronounced for the smile metric, for the brow raise, for the engagement metric. And that's maybe not entirely surprising, right? We know anecdotally that, you know, people are excited by robots, that people like to interact with robots. So you can see the smile, the brow raise, which is associated with excitement or surprise, and the engagement metric. Those are the ones where it's strongest. But even in the others, you can see that they're a little more emotionally expressive across the board. What's really great, and what I really just want to highlight, is that even though this is a result that anecdotally, you know, people in the field were aware of, it's really only because of the Aftex software that we're able to get a really quantified and very fine-grained quantitative estimate of this. We can show it quantitatively, and it's totally automatic. That's another thing that I want to call out. You know, previous research that people have done trying to estimate the emotional states of people, often that'll be done through video coding. You'll have someone sit down and kind of assign a label to different segments of a video, maybe say, you know, low, medium, or high smile, low, medium, or high engagement. But with Aftex, we can really get very fine-grained. I mean, 20 frames a second is just leagues ahead, and it's fully automatic, and it's objective. You know, there's no human subjectivity that goes into it. So I just want to call that out as, you know, being a big step forward in the kinds of analyses that we can do that enable us to get these results. We also look at the different models. So we had these, you know, this emotion-augmented model up at the top, and then we have sort of the standard model down at the bottom. And we compared the fit of those two to the data to kind of see which model is better at estimating a student's true state of knowledge. We do a little, you know, this is sort of how we train the model based on the data. I won't go into that too much because I know, you know, this is a short session and we've got a lot of other exciting stuff to talk about, so I'll just kind of breeze through this a bit. But essentially, we train the model based on the affective data. We compare that to a model that's trained on just the right or wrong answer data, and then we compare that to, you know, the actual ground truth that we have. And this is the second results slide that I just want to show you. So what you can see is for each of these are different skills. Each color is a different skill that we were tracking. And on the left-hand side of each color, you can see those dots are essentially the likelihood of the data under each model. So on the left-hand side, that's the likelihood of the data under the standard model. And on the right-hand side, you can see that's sort of the fit of the data, if you want to think of it that way. You can think of it as how well does the data fit the affective model. And you can basically see across all the scales except for maybe the third one, the affective model fits the data much better, which means it's better able to predict, it's better able to generalize to a larger population at estimating their knowledge state. So this is really exciting data. It's heartening to see that, one, people are producing better, richer affective data while they're interacting with a robot compared to just a tablet. And two, we can actually use that rich affective data to train better models, develop better algorithms for robotic education tutors. And this is another result slide that just kind of aggregates the data that you saw in the previous slide. So these are two main questions. Are children more emotionally expressive when interacting with robots? Yes. Can we leverage that emotional expression data to create better student models? Also yes. And just kind of bringing it all back to our original sort of vision. This was a physically embodied robot tutor that senses and understands emotions. It builds models of students based on affective data. But in this project, we didn't close that loop. The robot didn't act adaptively based on the affective data. So this next project that I'm going to show you has to deal with kind of tackling that piece of it. So this is Tyga, the robot that I kind of showed you in the first slide earlier. It's significantly more robust. It's designed to interact with children. It's designed to be out there in the real world. And this question at the bottom, that's kind of what we were trying to tackle with this next project. So these student models that we built in the first project, that allows us to personalize curricular content. What questions should I introduce next? But with this project, we wanted to ask a different question, which is how do you personalize affective support? So just like a good tutor, you kind of pose questions to the child, you see what they answer, but another part of what they do is also kind of making sure that the child feels comfortable taking risks, making guesses, that they don't get too discouraged or too overconfident based on how they're doing. And that's what we're trying to tackle here with this next project. So affective personalization of a social robot tutor for second language learning. It's a lot of text. I'll just kind of give you the high-level overview. We took this robot to an elementary school in Lexington over the course of 6 weeks. So it's a very long-term study. And we had, the robot there playing a game. Affdex was sensing their reactions to the game through the entire time. It was all synchronized. And we used the affective response to influence the robot's behavior in real time during the game. That's really, I think, sort of the core contribution here. So you can see a little bit about how the setup was. This was in a classroom. The logistics of this, were just, phenomenally complex. But we've got the robot, the game, the Affdex system, which is running on a separate phone here, which kind of ensures that we have a clear, consistent shot of the face. We have since integrated it into the robot's internal camera. You see that little dot at the top of the robot's head. We have integrated Affdex into that camera, but because the robot's moving around so much during the interaction, we want to make sure that we're always getting kind of a clean shot as opposed to sometimes on, sometimes off with the robot's camera. Just to kind of keep this centered around Affdex, because I know that's why you're all here, what the Affdex integration was doing was it was in real time, detecting the facial expressions of the students as they play the game, and it was using those emotional metrics as a reward to a reinforcement learning algorithm. So just a brief note on reinforcement learning. Reinforcement learning is a whole class of algorithms that's really experiencing quite a resurgence. If you heard about the AlphaGo, the system that Google built that learned how to play Go and beat the world champion a few months ago, that also used reinforcement learning. So it's a very powerful technique that's kind of having a resurgence right now. Essentially, it's an algorithm that learns based on reward signals. So you'll take a step, you'll take some action, and then you'll get a signal back from the world, whether that action is good or bad. And over time, you learn sequences of actions that are, successful or things that are unsuccessful. And that's what's novel here is that the reinforcement learning algorithm is actually learning in real time from real emotional data as the reward signal. So if the child is smiling, if the child seems more engaged, the robot learns, hey, that's something good, that's something I should do more. This is the game that we had children play. So again, very similar to the game from the previous project. The child kind of moves stuff around in this world, and then at various points is prompted to speak a word in Spanish or identify, let's say if someone says, can you find me pelota rojo? Child needs to tap on the red ball in order to advance. All right, so yeah, that's the game here. As the student plays through the game, the robot is providing affective support. So the robot, if you get the question right, the robot might say something. If you get a question wrong, the robot might try to boost your spirits. But, it depends. You don't always want to be, too supportive. Sometimes you want to push the child. You want to challenge them maybe to go a little bit beyond their comfort zone, to be in that flow zone instead of in the boredom zone, from that diagram that I showed you earlier. All right, this is a little bit of the math on the reinforcement learning. The important thing to know is that you can see here what the reward signal looks like. So it's based on a combination of engagement and valence. And because those are two things that we want to promote in any educational encounter. We want the child, obviously, to be engaged in the game. We want them to be, in that flow state. But we also want them to have a good time. We don't want them to be too frustrated. We don't want them to, even if they're learning a lot, we want it to be a positive experience so that they keep coming back. At the same time, it's important to notice that there are balances. It's not all just about having positive valence, in fact, I'll tell you a funny story that you won't find in the paper. Originally, we just had it based on valence, and we thought, yeah, the role of the robot is just to support the child, keep them feeling good as they go through this interaction. And what we found was that the robot learned to just make funny faces because that would cause the kids to laugh, the valence would shoot up, and the robot would learn, oh, that was really good, I'm just going to keep doing that. So we ended up, for the final deployment, balancing out that with this engagement term so that it's not just about, entertainment, it's also about, focusing on the educational interaction. I'll show you real quickly a video just of some of the things the actions that the robot could take, and you'll also get to kind of see, what the robot actually looks like on the inside. So in the back, you'll see it kind of has this fuzzy red skin with a little tuft of hair, kind of looks like a Dr. Seuss character. That was on the robot during the interaction, but here you'll kind of get to see what it looks like and the sort of cool mechanical internals of what that looks like. So that's a frustrated look. This is a little more inquisitive. That's kind of an excited, action, encouraging the child. That's a confusion one, so you can kind of see the robot's like, huh, why'd you do that? That's sort of a tired expression, a little bit of a sad. Right, so you can see the robot is, it's producing these very sort of interpretable emotional expressions that, it's easy for kids to pick up on what is it that the robot is trying to communicate to me. They, in turn, will respond emotionally to that action. And then the robot learns that the children's response gets sensed through AppDeck and feeds back into the robot's action selection policy through the reinforcement learning algorithm. All right, so what did we see affectively from this? Well, one thing we saw, these are the sort of before and after results. So you can look at engagement and valence and what happens before the robot does, before and after the robot does these different actions that you just saw. So when the robot does the yawn, you can see, yeah, engagement drops. And this is a really great validation for us because it lets us know the child's emotional reaction is indeed influenced by the robot's action. So it validates to us that children are picking up on what the robot's doing, and that in turn is influencing their emotional state. So you can see engagement drops off steeply after the robot does a yawn. It picks up though, and valence picks up after the robot does a sort of a positive yes. You can also see the valence picks up after the robot does a yawn simply because it's it's kind of a compelling, exciting action that the robot takes. The valence drops after the robot does a sad animation, which is great. You see there's this sort of emotional mirroring that's happening. And when the robot does that kind of quizzical, interested one, kids also, their valence picks up as well. Here's, I think, maybe the most important graph of the whole thing. So as I said before, we did this experiment over the course of 6 weeks in a actual preschool. And one of the things that's well known in human-robot interaction studies is that there's a very strong novelty effect, that when people first see a robot, they're really excited and they treat it in a different way. But over time, if you interacted with it every day, you kind of exhaust the space of what it can do. It becomes a little more boring. We notice that engagement dips down over time. So this is the valence over time between the first session and the last session. And as I said, we ran two conditions, one in which the robot was learning from the child's emotional expressions, and one in which it was kind of just choosing randomly. And you can see a very strong effect here where between the first and the last session, the non-personalized robot, the valence just drops. I mean, it actually ticks down to below 0. So that you can see in the first session of the non-personalized robot, yeah, kids were very excited about the robot. They interacted with a lot. They were, they had this positive valence feeling towards it. But by the end, it dips down to even below 0. So kids are they're kind of bored with it. They don't want to interact with it anymore. Whereas when you look at the personalized robot, it's obvious that, okay, it starts down a little lower because it's still learning, but over time, that actually grows. The valence actually grows. So our takeaway from this is that appropriate affective responses are really critical to avoiding this novelty effect. And I think that's something that's very cool. That's something that we're going to continue to explore. And I think it's a really foundational result, for further exploration of affect-aware social robots. And then, of course, because this is an educational study, we wanted to see whether they actually learn from this. And you can see across a whole wide variety of vocabulary words, kids did actually learn how to speak a little Spanish. So that's great. All right, so these, just to kind of sum up the contributions of this study, it was a long-term interaction study with a fully autonomous social robot. We actually ran the experiment inside a classroom. We did affect personalization with Affective. We ran it on a very difficult population to work with. So the social robot, it personalized its affective response. The children's valence over the long term increased as a direct result of that affective personalization. And that's really cool. All right, I want to give some time for questions, so I'll maybe just wrap this up and kind of talk about some of the stuff that we're doing here at Jibo, where what I see the future being is I see that old challenges are becoming tractable. The problems with doing this kind of affective research before, it was all in the sensing. No one had good ways to reliably get fine-grained and accurate estimates of affect. But thanks to Affectiva, that's possible now. We're able to get the sensing problem is largely solved for the kinds of problems that we want to do. And that's phenomenal. That kicks open the doors to really tackling a whole bunch of deeper questions. So the new challenges for us when we think about how does affect integrate into a robot's cognition, they're conceptual, they're computational. We want to think about how does a robot like Jibo, a consistent coherent robot character, how does he perceive, react to, and think about the emotions of the people that it's interacting with, that it's sensing, and that's very exciting. I just want to real quick shout out to my collaborators, because this project was, these projects were not done alone. No one could do these projects alone. Professor Cynthia Peel, Goran Gordon, Jackie Corey, Luke Plummer, Jinju Lee, and of course the NSF who funded the majority of this work. So thanks to them, and thanks to you for listening, and I'll take some questions now. I don't know if there's a way for people to ask questions.
Hi, Sam. There is a Q&A box on the top.
Q&A box.
Go to the top ribbon, drop-down menu. And then there is Q&A.
Under options.
Under options. Oh, yeah, I see it. Great. Excellent. Sorry. Okay. Yes, great. What is the engagement metric calculated based on facial action units? Yes, it was calculated based on facial action units. I'm sure someone from Affectiva could actually tell you what specific AUs they're looking at, but for us, I'm sure the brow raise is an important one. I'm sure probably it takes into account the orientation of the face to the camera a little bit. I'm sure it, is sort of based on, yes. That is, as far as I know, directly provided by the Affectiva SDK. At least it was at the time that we were using it. And actually, between, engagement and valence, I think we found to be among the most useful of the metrics. Let's see, Amina, I saw that you asked a question, how can you support researchers in the emotion field? I think, Affectiva has done a tremendous job of that, like I kind of alluded to in that last slide. This is research that would not have been able to be done 5 years ago, simply because you wouldn't have been able to get the kind of data that we were able to get at such a fine-grained level and with a real quantitative and objective metric. Sahil, I want to know if you were able to measure any learning gains among children using the affective personalization versus no affective personalization. We did look at that. We did not see any differences in learning gains based on affective personalization and no affective personalization. But we're not entirely surprised by that because the role of the robot in that project was a little bit different from in the first project. So the role of the robot in the second project was not to necessarily introduce, new questions or to sort of guide their learning. It was more to provide emotional, affective support to keep them engaged. We would have, if we were looking to really maximize learning gains based on affective personalization, we probably would have chosen different variables or introduced new things into the reward function because the algorithm really is it's optimizing that reward function. So if we kind of go back to that slide that shows what the reward function is, it's based on engagement and valence. So it's based on those two things, not necessarily on making sure that the children are getting questions right or wrong. And that kind of goes to, we know about curricular personalization, and this was really trying to take a different type of personalization, tacking more towards affective support, making sure that kids feel like they're, supported and having a good time. Okay, any other questions? Oh, also, were you measuring only valence or other cognitive states such as frustration and confusion very relevant in a learning context? Yeah, absolutely. At the time, I don't believe the SDK supported a frustration or a confusion. We were using brow furrow as a proxy for frustration, So we were looking at that, and they are absolutely very relevant in a learning context. I believe in the 3.0 SDK, which we are just now starting to kind of dig into, frustration and confusion are supported cognitive states. And I think, let's see, we're already a little bit over time, so maybe this will just be the last question. Based on your studies with kids, what is your hypothesis on how engagement and the novelty effect will change with adults and elders? Yeah, so one of the things that I guess I'd say about these two populations is that kids are very willing to kind of forgive the robot for certain things. You know, kids, they're a little all over the place, right? You know, they kind of, they're not as concerned with if the robot kind of says something that doesn't make total sense. And so in that regard, I think they're a great population. Adults, elders, I think they might be a little less forgiving, you know, of a little bit of incoherence in the robot's behavior. They might expect to be able to talk to it a little bit more. They might expect it to sort of have a little like deeper intelligence. And so we'll have to make more progress in different areas, I think, before it's ready for, in order to see the same kinds of things that we've seen with the children. And that's stuff that we are actively working on at HighLevel. So I'm optimistic that we'll be able to sort of extend this to all populations in the future. All right, I think that's just about my time. I will be on the lunch Q&A interview session, so if you have more questions, I'll be happy to answer them then.